any questions at all, you can type those into the chat, and we'll deal with questions after his talk is done. So thank you so much for joining us, and please go ahead, Rob.
Okay, good afternoon, everyone. I'm going to present a short lecture on evaporation, and I will include resistive thermal evaporation as well as electron beam evaporation. I view this as a refresher. I usually give a more detailed talk that usually takes somewhere around 3 hours on these two, but I want to try to condense this down to an hour, including questions. I invite you, though, if you have any serious questions in these matters, please get in touch with Mark, and Mark can put you in touch with myself or someone that could help you. I have my contact information on this slide as well, and maybe the slide presentation or a recording of this can be made available later if need be. So what we're going to cover today, as I said, is resistive thermal evaporation and electron beam evaporation. They're kind of tied together. One kind of technique builds on the other, and I will do my best to explain what you need to know in order to perform these things. First comment is safety, because you know, a serious matter is that I've known 2 people personally that have died using PVD equipment, and that's as many as I want to know. I don't want to know of anyone else that has died because they've touched the wrong thing at the wrong time. Way back when, this was a very wild and woolly kind of technology, and a lot was left to the imagination. But today, a lot of safeguards are built into equipment, and I'm happy to see that. So hopefully, like I say, there is a lot of caution that needs, and a lot of respect that needs to be rendered to PVD equipment. Also, a lot of people don't think of it, but in evaporation processes, there's bright light, and the bright light can get quite intense, and there are ways to protect you from overly bright light by using things like welder shade. We use welder shade 9 here in Lesker when we're looking at bright evaporation processes. So let's start on thermal resistive evaporation. Evaporation is a process where you're going to take a solid material and you're going to vaporize it one way or another, and then that vapor is going to condense out on the substrate and make a thin film, hopefully. Thin film thicknesses and properties are an end product of this process. Liftoff is generally the intent of most evaporation processes, and the reason why is because evaporation happens at a relatively low pressure, and you get line of sight deposition from the evaporation sources, whether it be a resistive source or an e-gun. The evaporation process should not cause excessive heating of the substrate, because that can be very injurious to photoresist, certain kinds of photoresist. There are a ton of different evaporation sources. How do you know which one to pick? How do you know which one to choose? We can give you some guidance. I'm sure you probably already have a general idea, but they're generally classified in 2 major categories. One is directly heated, where the material gets placed directly into boats, baffle boxes, or into spirals, or into coils. You can actually shove little pellets in the coils, and it does work nice. People have made canes out of certain evaporation materials, and they put them on loops to evaporate. The other kind of source is indirectly heated, where you put the material inside of a crucible, and the crucible then gets placed inside of a indirect heated source, a box heater or an LTE or an infusion cell, something of that nature, or a coil basket heater. Understand that the heat is generated by the resistive source, and it has to travel from the source through the crucible and then into the material. So the thermal conductivity path is a little indirect here, and that's why these are indirectly known as indirectly heated sources. There are many different considerations which source to use, which boat or box heater or coil to use. Geometric considerations are one, how the system is laid out, what size source can the evaporation posts hold, and that kind of dictates where to go from there. The size of the power supply is important as well. It's really important to know what the voltage and current outputs are for your power supply, and I'll get into that a little bit later, because it will define the boat or an adequate boat that you can use. Material compatibility is also an issue because certain materials, when they go in liquid form, can interact with boats. If they go into liquid form, they can destroy boats, they can destroy crucibles. I'll touch a little bit on that briefly. The type of material being evaporated also determines really which source is best. And bottom line is the thickness of the film also is going to dictate what size evaporation source or boat to use. Distance between electrodes. Here you see a cluster flange of 3 or 4 evaporation sources. And from post to post, the evaporation source spans. And this length is critical to know because if you're ordering a new boat or reordering boats, it's important to get the right size boat here. Otherwise, you're going to wind up trimming down boats or adding extension plates to hold smaller boats. It's also kind of important to estimate the how much material a boat or a crucible can hold, because that's intimately tied to how thick of a film you can make ultimately. The thin film uniformity is also affected by the position of these evaporation sources in relation to the substrate. This should already be set though in any system that you're currently using, and it should have been designed so that you get relatively good uniformity. So all of these evaporation sources, if you go to anybody that sells them, they will usually list on their website or in their catalog the voltage, the current, and the power that are required to get the evaporation source up to a certain temperature. These are useful numbers to know and consider when choosing a boat, a box heater. What happens if your power supply only gives off 2 volts max and it's limited to 200 amps? Well, if it's limited to 200 amps, certain of these sources require more than 200 amps to reach a critical temperature. So, you know, it's important to consider the output of your evaporation power supply. When it comes to material compatibility, one considers materials that sublime. Generally, they don't interact with the boat or the crucible that's holding them. And as a rule, they work fine in just about any kind of material, boat material or crucible material. Most materials that melt, they do stand a good chance of interacting with the evaporation source. So you have to be cognizant of that. Generally, experience is a good indicator. People usually know what kind of boat material works with a certain given material. Gold, palladium, nickel, they use generally alumina coated boats or alumina crucibles in order to heat them up. And we're talking resistive evaporation here, not E-beam. But the Al2O3 coated boats prevent the gold, palladium, or nickel from wetting to the boat, and you can pull the material out of the boat in many instances and many occasions after the evaporation is done, because the material does not wet to the Al2O3 coating. Titanium, common material done in resistive thermal evaporation. I tend to only use cheap tungsten boats that are at least 15 thousandths of an inch thick. And you can almost guarantee that with titanium, you're only going to get one use per boat because it is going to dissolve, interact with, and pretty much destroy the boat after one use. And generally the layer thickness after that one use, if you're shooting for 100 or 200 nanometers, it should be okay, but anything much more than that, it's not going to work for titanium. And I realize titanium is usually a thin layer. For aluminum, again, I use cheap tungsten boats. Aluminum makes any refractory metal boat crack very easily. It makes coils that evaporate it crack very easily. And generally with crucibles, we recommend boron nitride or pyrolytic boron nitride crucibles. Some materials are ill suited for evaporation, and silicon is one. Silicon in any shape or form is going to interact with any boat material once it starts getting hot and molten, and it will totally destroy boats, crucible liners, anything in its path. Once it's melted, it'll use up, it'll destroy. For organic materials, we recommend a temperature controlled source, temperature controlled instead of current or power controlled, because these organic materials generally require specific temperatures at which to run at. And that's something you're not going to do well with a boat source or a crucible coil basket source or anything like that. When we talk about evaporation, basically we're talking evaporation rate, and it's somewhat equivalent to the vapor pressure of the material. And the material's vapor pressure is dictated by its surface temperature. The hotter a material gets, the more it approaches its evaporation point, and the colder a material is, the less likely it is to evaporate. For normal deposition geometries, we consider a material vapor pressure of 1 × 10⁻² torr high enough to cause or give good deposition rate. And I'll show you a chart in a second that will cover that. But I'll use evaporation temperature, and by that I usually mean the temperature required to raise a material pressure to 1 × 10⁻² torr. Very helpful in any kind of evaporation is the Holonyak vapor pressure curves. I have copies of these curves if you would like, but generally they list all the elements and they give the vapor pressures of the elements, temperature in degrees C in the upper x-axis, and the vapor pressure on the left y-axis in torr. The heavy dashed line is the 1 × 10⁻² torr pressure. So if you heat a source up or you heat a material up so that it crosses this 1 × 10⁻² torr, at that temperature, you will get probably good evaporation. Always a good gauge, always a good piece of information to have. The dots on these curves represent the melting points of the material or the elements. So if the melting point is below this 1 × 10⁻² torr pressure line, generally the material is going to melt and then evaporate. If the curves are substantially above this line, that means the material most likely will sublime. It's good to know this because we get many calls from people saying, hey, I'm heating my material up and I'm not getting, it's not melting, but I'm getting rate. What's wrong? And the answer to that is nothing. The material is subliming. Some materials, when they evaporate, generate large particles, and you'll see this commonly with silicon monoxide, mag fluoride, most selenides, sulfides, and tellurides. And they have special boats to do these materials in if you're trying to evaporate them. And the idea here is that if we make the vapor stream change directions on its way out of the source, generally we'll filter those macro particles out and we'll get relatively pure vapor going to the substrate. and you will get a good coating on the substrate, hopefully, with very few macroparticles. Alloys, when you're thinking about evaporating alloys, they really don't work too well unless their vapor pressure temperatures are relatively equal. And by that I mean, if I go back 2 slides, if I can magically make an alloy out of, say, osmium and cadmium, if I start to evaporate that alloy, cadmium will start coming off at a temperature somewhere around 260 degrees C. Osmium is not even going to feel, it's not even going to sneeze at 260 degrees C. So if you heat an alloy up like that, basically you'll get all the cadmium coming off and you'll be left with a clump of osmium. More or less that's true. There are some liberties taken there, but more or less that is true. Again, as we covered, organics are better done in a temperature-controlled source where you can apply power, monitor the temperature. There's a thermocouple inside these sources. The crucible sits on the thermocouple, and you'll be able to heat the source up based on temperature. Refractory metals, a lot of people say, hey, I want to resistively evaporate tungsten or tantalum or platinum or something that's very high temperature material. Most of those are better done via E-beam, and some of them are quite impossible via resistive evaporation. So I want to caution you, I have a way of doing evaporation I've developed through the years. It's my way, it's not the only way, and I'm going to tell you the way I do things. And please take it with a grain of salt. I'm more interested in the theory behind why I do what I do, but the exact procedures of how I do it, I'll leave that up to you. You decide how you want to pattern your evaporation runs, and these strategies apply to resistive thermal evaporation as well as E-beam evaporation. And I will cover it again when we get to the E-beam section. Number one is always do a manual calibration run on any new material. If you're running or evaporating a material for the first time, I am always cautious. I put it in a boat. I start to run up the power manually. I see how the material interacts with the boat. I make sure that there's no compatibility issues. I'll slowly ramp the power up on the source until I get a decent evaporation rate coming off of the material. And I will record the power that I get the evaporation rate at. So that's a very important thing to do. It's a very important thing to note. Evaporation is always done in tandem or in cooperation with a quartz crystal monitor. The quartz crystal monitor is calibrated as well to read a relative rate. And then in a automatic feedback or a PID loop control, the quartz crystal monitor will tell the evaporation power supply how hard to run, how light to run, based on the reading of the quartz crystal monitor. Second suggestion is to set reasonable ramp and soak power levels based on the manual calibration, and strive for reasonable deposition rates. It is possible to evaporate materials at quite a high rate, either with resistive thermal or electron beam evaporation. But usually what happens is it allows you to make a very poor film very quickly. Reasonable evaporation rates, 1 to 3 angstroms a second, 1 to 5 angstroms a second. The smoother a process runs, the better the film will turn out. And if you're trying to shoot for too high of a rate, you're going to have control issues more often than not. And the only exception to this, really, there are 2 materials that are common now, indium and lithium. And generally, people are trying to shoot really thick films of indium and somewhat thick films of lithium. Indium is used in underbump metallurgy, and lithium is used in thin film battery technology. And some of these films can go from 2 to 20 microns thick. So if you can appreciate, if I run a 20 micron thick film at 1 angstrom a second, I'm going to be 30 years older by the time that that layer finishes. And I don't want to do that. So in these instances, it's quite allowable to shoot for evaporation rates 50 to 100 angstroms a second. It does produce a very rough film, a very flawed film, but in these applications, it's somewhat acceptable. There are secondary processes that can be done to these films to try to smooth them out a bit as well. So a manual ramp soak, and this is the layout of what I do. I slowly increase the power of the evaporation source until I hit my desired deposition rate, and I record that power level. And generally, most controllers allow you 2 ramp soak levels, ramp 1, soak 1, ramp 2, soak 2. And at the end of soak 2, I want to have the material conditions such that I am already at my evaporation rate. That way, when I go to PID loop control or auto rate control, my PID loop does not have to search for that control point. It's there. Generally, this produces a relatively smooth transition between the manual ramp soaks and the PID loop control. The one thing you're trying to prevent is oscillation of the power when you go into PID loop control. And generally, that oscillation in power is caused by soak 2 ending at a power much lower or much higher than the desired deposition rate power. This oscillation of power can be very destructive to both the boat or crucible holding the material, as well as injurious to the film that you're trying to make on the substrate as well, because in these wide power swings, you'll get material spitting. Generally, you'll get large particles included in your films at this time. Some of the quirks and qualms to any kind of evaporation process is that if you have to vent the system, sometimes the materials that you're evaporating can form oxides or nitrides readily when it's exposed to ambient air. This might require an additional ramp soak in order to first burn off or burn through that oxidized or nitride layer when you go to reuse this material. So try to keep that in mind. Generally, if something evaporates at, say, 20% power, and it's consistent 20% power run after run after run, and all of a sudden it's taking 30% power, there's something wrong there. Either there's not enough material in the boat, or maybe the material is oxidized or nitrided. Just keep that in mind. Not everything runs off of a 2-stage ramp soak. Some things need 3 steps or maybe even 4 steps. So thermal evaporation, E-beam evaporation is light of sight deposition. That means the mean free path in the chamber is quite large. Things go straight from the evaporation source. And this is what makes it very attractive when it comes to feature filling. Atoms, though, have less than 1 eV of energy on arrival at the substrate. And this means that film formation can be kind of clumpy. And I'll touch on that a little bit later. But there are ways to augment this energy level either through ion beam assist or heat on the substrate. Either one can work. You're trying to get a higher energy level so that atoms have more motility on the substrate and are able to form a smoother film that way. Rate control generally is dependent on a quartz crystal monitor. It's very important to set up quartz crystal monitors correctly, and I may have the opportunity to touch on that at the end of the talk. In resistive thermal evaporation, and this is what's different from E-beam, in resistive thermal evaporation, there's no loading or fill requirements. Basically, you only put as much material in as you need to make the thickness layer, or the film thickness that you require on your substrate. And you know, one can do that that calculation as well, and I will touch on that later. But basically, on the Thornton film growth model, you're dealing at the low energy level with thermal evaporation. So basically, you're getting columnar film structures that can be smooth or not. Generally, you're in zone 1 or zone T, early stages of zone T, depending upon the material. Everybody tries to work toward Frank Vandermeer type film growth, but generally resistive evaporation, low energy level, you're going to probably get a combination of Boehmer-Weber and Frank Vandermeer type film growth. An important factor in any evaporation process is what base pressure do you start at? And I ask this question of most anybody that I encounter, especially if they're having trouble with film quality. What's your starting base pressure? And basically by that I mean that if I start my evaporation process at 1 × 10⁻⁶ torr, the natural arrival rate of water vapor coming off of the walls at that base pressure is enough to accrue 1 monolayer of water vapor at the substrate every second. That's a very heavy duty water vapor flux, and there's very little you can do about it. There's 2 ways around a high water vapor flux. One is pumped down to a lower base pressure. At 1 × 10⁻⁷ torr, I form 1 monolayer of water vapor at the substrate every 10 seconds. At 1 × 10⁻⁸, I'll form 1 monolayer every 100 seconds. So I can pump down to a lower base pressure, or I can run at a higher evaporation rate, and that will tend to dilute the contaminant water that's present in the vacuum system. Common problems with resistive thermal evaporation are stress on the boat, the basket heater when tightening down the source into the system. There is a trick there. You want to try to keep as much torque off of the boat or the basket heater that you're using as possible, and still get a good tight connection between it and the evaporation post. Generally, when somebody has trouble with excessive power requirements, one of the things that might be occurring is they don't have the ends of the boats tight, or the electrical connection made well enough between the post and the boat. You can also overfill evaporation boats, and this is especially true the smaller the boat size gets. Ultimately, you can bridge the distance between the electrodes with the material that you're trying to evaporate, especially if it goes into liquid phase before evaporating. So picture, if you will, a small boat filled with 20 copper pellets. If I heat the copper pellets high enough so that they melt, I can get a bridge of copper between both copper electrodes, and the resistance of the boat will go down. You'll need a lot more current before I can get the copper to evaporate finally. And I might be out of the current range of my power supply. Likewise, if I try to use too large of a boat for my power supply, if a boat requires 200 amps to get to 1300 degrees C, and I can only give it 100 amps, I'm not going to get my material up to 1300 degrees C, and it probably won't evaporate. So you can use too large of a boat as well. Another common problem is trying to get stable film properties when using too high of an evaporation rate. Some people whack at thermal evaporation for the first time and they say, hey, I want to try to run at 30 angstroms a second and see what I get. It's very hard to control at that high of a rate. So you'll get oscillations in power usually, and then B, the film will come out quite rough. Also, you know, as we covered, you can get material boat interactions. Certain materials are very hard to run in a resistive evaporation kind of a setup. not much you can do about that. Also, a bad fit between the crucible, if you're using a crucible, and the source, whether the source is a box heater or a basket heater. If the crucible is too loose inside that heater, you're going to have a hard time controlling the rate. The rate will become unstable. Also, if the fit's too tight, you might wind up cracking the crucible liner as well. How much material do I load in the source? If I only need to put in the evaporation boat, if I only need to put as much material as I need to make a film of a required thickness, how much can I calculate that? And the answer is yes. If one views the distance between the boat and the substrate as a hemisphere, if I calculate the surface area of that hemisphere and then add to it the thickness of the film that I would like to do, all in terms of centimeters, then I can get a volumetric calculation as far as how many cc's of material I need in order to create that layer of a given thickness. I usually add about 20% more to that in order to be safe. But it's quite easy to calculate. So that's a quick tour of thermal evaporation. If anybody has any questions, if you can save them to the very end, that would be good. And if there is no objections, I'll continue on to electron beam evaporation. Okay, in electron beam evaporation, this is a picture of a typical E-gun setup where you have the high voltage feed through, the E-beam gun. You'll have a secondary feed through over here to control the electromagnet in the E-gun as well. You might even have a quartz monitor cable coming out attached to a quartz crystal monitor. This is a neat picture of electron beam crashing into the pocket that holds the material. And this is a little bit better diagram of how this actually happens. You have an electron emitter, which is a tungsten filament. You run a relatively low voltage high current through that tungsten filament. You bias it with a high voltage as well in reference to the anode section here. And what happens is an electron beam will start coming out of this filament. This beam is somewhat guided by the anode optics. It's also guided by a permanent magnet that sits in the back of the electron, the E-beam gun, usually. And the beam is curled or turned via the magnetic field, and it's steered by an electromagnet that usually exists in front of the gun to create the sweep patterns. Very basic view. The thing to note here is that the electron beam gun is actively water cooled, and the hearth pocket that the crucible sits in is actively water cooled as well. This tends to keep the crucible liner, the material holding crucible liner, relatively cool. So the interactions between the material that I'm E-beam evaporating and the crucible liner are somewhat minimized by the fact that this crucible liner is being water cooled. It's been my claim that electron beam evaporation is probably one of the most complicated techniques in PVD. It's not well understood. People understand, hey, I push a button, the power comes on, beam is generated, and poof, my material evaporates. It's actually a lot more complicated than that. The other drawback to E-beam evaporation is usually it runs off of relatively high power. And at high power, the danger of damaging the E-gun or damaging the system increases. So E-beam is a very useful technique, but it can also be a very destructive technique if you don't use it or don't understand it. Most any material including refractory metals, can be E-beam evaporated. But higher vapor pressure materials, materials that need very little heat to get large vapor pressures, usually not a good choice for electron beam evaporation. If you can understand the thermal conductivity through the E-gun, you will be able to evaporate any material that you want in an E-gun, even using a relatively small power supply on the E-gun. Thermal conductivity through the E-gun is very important to understand because it'll explain any kind of aberrant behavior that you might see. Basically, when the beam hits the material inside the crucible liner, the heat is transferred through the material, through the crucible liner, and then into the water-cooled hearth pocket, and hopefully out of the coolant into your cooling system. Any change to the thermal conductivity of this system as it exists, you see a large fraction of energy going in, a relatively small fraction of energy being carried out through the coolant line, and most of the other energy goes into evaporating the material. So any change to this intrinsic thermal conductivity path will lead to changes in power to get a given rate. A lot of people have problems with consistent power for a given evaporation rate in E-beam, and generally it's because the thermal conductivity equation has changed in the E-gun. A couple of different ways that can happen is if the crucible liner cracks, you can get material leaking out of the cracks and that touch the hearth pocket directly. When this happens now, it'll require more power to get to a given evaporation rate, primarily because the thermal conductivity has increased and more power is going into the coolant and less power is staying resident in the material. Also, if I overfill the crucible liner, I tend to splash over the crucible liner, and the material can then directly touch the hearth pocket as well. And this creates a good thermal conductivity path. And again, I'll need more power to evaporate the material at a given rate. Some people are very poor housekeepers, and they can let material accrue in the hearth pocket area. I've even seen an instance where somebody left a pellet in the pocket, tried to put the crucible liner into the pocket over top of the pellet, and got all sorts of disastrous results because of this. So in these instances, the thermal conductivity path in the E-gun has changed, and it will cause a change in the evaporation rate. So E-beam evaporation guidelines are basically the same as the resistive thermal guidelines. A smooth process, you're always desiring a smooth process. You have a couple of different manual ramps and soaks that you can play with. Also, you need a quartz crystal monitor to help you control the rate. There is a fill requirement on these crucibles that go into the E-gun. Generally, as a rule, you want to make sure the crucible is at least 2/3 full of material. A lot of people, when they go to E-beam gold or platinum, might only put 1 pellet or 2 pellets in the crucible. It can work that way, but generally what happens is the beam interacts with the crucible and you wind up contaminating your material or destroying your crucible liner. Generally, as a rule, I like to use higher voltages if you are running an E-gun where you can change the voltage. The higher the voltage is generally used for metals, 8 to 10 kV, and then lower voltages are usually reserved for sublimating materials. Key here is when you change the voltage in any given pocket, you have to redefine the beam limits. If you don't redefine the beam limits, your beam can wander in or out of your pocket. So if you change the voltage that a pocket works at, it's very important to reset the pocket limits. People are overly fascinated with the ability of an E-gun to sweep its beam. I try not to pay a whole lot of attention. Generally, as a rule, I use a sweep for sublimating materials. I try to make for materials that sublime like Al2O3 or SiO2 or even chromium. I try to use as a diffuse sweep pattern as I can make. And generally, the E-gun allows you to do various things to diffuse the sweep. And I also use a very slow frequency and a relatively large amplitude for the sweep. This is all in kind of an effort to abate core drilling through the material. It's quite possible to center core drill through sublimating materials and then drill a hole through your crucible liner before you reach your layer thickness goal. And you don't want to do that. You endanger the E-gun when you do that. I use a sweep to pre-melt most metals though. Usually for some metals, they don't melt at relatively low powers like titanium. And what I'll do is I'll fill the crucible liner up with titanium pellets, and then I'll pre-melt. I'll manually ramp the power of the E-gun up, and then I'll manually steer the beam around the pocket to pre-melt the titanium. My theory on this is the smoother the surface of the melt, the more consistent my evaporation is going to be. Not quite possible with sublimating materials, but with metals that melt, I can do a pre-melt, and usually the evaporation process runs smoother that way. I do use a sweep for aluminum when I'm E-beam evaporating it though, and I'll usually use a relatively high frequency, and by that I'm talking maybe 30 or 40 hertz in both X and Y, and I'll use a relatively low amplitude, and this seems to work better for aluminum. And for refractory metals, I'll usually use a rod form of the material. And you can buy refractory metals, you can buy any material in a rod form or a pre-melted slug. And I'll use a fixed focus beam on the rod in order to evaporate refractory metals. It works better. I can get a relatively good rate out of a refractory metal in rod form. The rod just keeps away from the side walls of the crucible liner and allows the material to retain more of the heat. The danger is with high temperature melting materials like refractory metals, they don't melt well into themselves. And it's quite possible that if you start with pellets and you increase the beam current, basically the pellets move out of the way, or they slough out of the way of the beam, and it's really easy at that point to drill through the crucible liner and into the hearth pocket. So if you ever have to E-beam refractory metals like tantalum, tungsten, iridium, let me know, because I have a way of doing it, and generally it involves rods of the material rather than pellets. This is a picture of something that I did. Basically, I had, I believe this was molybdenum. I think it was moly pellets, and I turned up the heat, and the pellets just sloughed away as they were melting, and it exposed the bottom of the crucible. And this happens in a few seconds. This can happen in a few seconds at high powers on your E-gun, and the results can be quite disastrous. The same basic plan is resistive thermal evaporation. When I'm dealing with a material I do not know, I will always do a manual calibration where I'll run the power up on the E-gun manually until I hit my desired deposition rate. and I'll note that power, and that'll be my ramp 2 soak tube power. Basically, this is in an effort, again, to get a very smooth evaporation process once I go into PID loop or auto control mode. In E-beam evaporation, if I get oscillations when I go into PID loop control, these power oscillations, I can go from liquid to solid quite rapidly for the material. And if the material wets to the crucible liner like aluminum, these rapid transitions from liquid to solid over the course of a couple seconds will tear apart any kind of crucible material. And it'll happen to metal crucible liners, it'll happen to graphite crucible liners. So the point of this is you want as smooth an evaporation rate once you go into PID loop control as possible to avoid these power cycling, power ringing kind of events. With electron beam evaporation, you can get ungodly rates if you want. I've tried and I've gotten 200 angstroms a second easily with aluminum using an E-gun. At those higher rates though, the films come out terrible. I can't overemphasize that enough. And generally I've been doing E-beam for quite a long time. Most of the films that I've made usually work better at relatively normal rates, and I classify that as between 1 and 5 angstroms a second. On E-beam, it's quite easy to control the rates on good metals, good thermally conductive metals, down to 0.1 or 0.01 angstroms a second if need be. And I've done that as well. It's just a matter of doing the manual calibration and having a good calibrated quartz crystal monitor. However, when you're doing materials that sublime, it's generally easier to set the desired deposition rate a little bit higher, between 2 and 5 angstroms a second, because sublimating materials don't happen off of a very controlled, smooth surface. They happen off of a very irregular shaped surface, and the thermal conductivity through that material is very poor. So sublimating materials like Al2O3, SiO2, generally in an E-gun are going to require very low powers because the thermal conductivity through the material is going to be quite low. All the heat resides or plays on top of the material, and it causes the rates to go up quite high for a very low power setting. Sublimating materials, I generally try to set the voltage down as low as I can on the E-gun, which gives me a little bit better current resolution and better control over the rate. I can explain that if need be in greater detail. Basically the same kind of film growth model. E-beam evaporation, the atoms still have less than 1 eV energy when they get to the substrate. So usually if I'm trying to make super smooth films, I'm going to need to heat the substrate or maybe even let an ion gun assist help me out there as well. There are many kinds of crucible liners, all sorts of different materials, from metals to insulators to graphite, fabmate. Which one do you use for a given material? That's a hard thing to explain. Generally, as a rule, I pick the cheapest because I'm kind of cost conscious here. And generally, that's going to be a graphite or a fabmate crucible liner. The more exotic the material gets, the higher the price of the crucible liner. And there are also thermal conductivity considerations as well. A graphite or fabmate crucible liner is going to be less thermally conductive than moly or tungsten. And if it's less thermally conductive, that means I'm going to require more power for a given deposition rate when I'm running a material in a tungsten crucible than I will to get that rate in a fabmate crucible liner. So all of this is a strategy you can use. The one thing that I will tell you is I cannot recommend using an electrically insulating crucible liner in an E-gun. It produces all sorts of charging effects, and you run into all sorts of weird and flaky problems when you're using an electrically insulating crucible liner in an E-gun. So my recommendation on that is make sure always that you use an electrically conductive crucible liner when you're evaporating material in an E-gun. Again, carbon and fab mate for most materials. Generally, as a rule, I do that. Don't use dielectric crucible liners. They will work on insulating materials. So you can run an Al2O3 crucible liner on Al2O3 or SiO2, and it will work. But you will still get charging effects, and those are quite distressing at times, and they cause different effects in the film as well. So a recommendation when you're even doing dielectrics is still use an electrically conductive crucible liner. So when people use carbon crucible liners or graphite crucible liners and they evaporate gold or platinum, there are a lot of reports of carbon contamination in the melt itself. And generally when that happens, as I've explained before, people are only putting 1 or 2 or 3 pellets of gold or platinum inside the crucible liner, and it's dramatically underfilled. And as a result, the beam plays off of the graphite crucible liner and the material as well, and it gets carbon inside the precious metals. And when that happens, generally as a rule, you'll get a lot of spitting, and usually that's manifested in little balls of gold, balls of platinum inside the film. And you'll see film just totally replete with little balls of gold or little balls of platinum. So bottom line is crucible filling when it comes to precious metals is quite important. So E-beam as a rule, ramp up in power with a lot of care. Make sure you ramp up in power, ultimate power at a relatively reasonable rate. Ramp down in power when the deposition is done as well. If you all of a sudden turn off the power, say like I hit my film thickness and I just, in the program or manually, I just turn the power off right when the deposition is done, that instantly cools the material down. And generally that can lead to a cracked crucible. So I generally cool the crucible down at a slower rate than I normally ramp it up. A lot of people crack crucible liners when it comes to E-beam evaporation, and you know, a lot of it is tied to procedure, turning the power off, or not coming up with good ramp soak levels for when they go into PID loop control. Another interesting fact is silicon will destroy the crucible liners as well. Even though the crucible liners are relatively cool, as soon as the silicon goes into liquid form, it'll wreak havoc on the crucible liner. Silicon is also an interesting material in that it'll start growing up toward the beam. And I have seen, or I've actually done silicon in an E-gun directly in the pocket and had a giant cone of silicon grow up from the melt such that I could not rotate the pocket to get to my next material. So silicon is just a weird material to E-beam evaporate. What I recommend for silicon, if you've got to make a thin film, is either CVD or a magnetron sputtering. A lot of people tell me that they have trouble with magnetic materials in an E-gun. I've been doing E-beam evaporation for many, many years, and I've never had a problem with magnetic materials. Materials like cobalt or iron in an E-gun, not really a problem. A lot of people think they'd interact with the magnetic field in the E-gun, and to a certain extent they do, but it generally is not a problem. Again, just to outline what I recommend for E-beam, special suggestions. Refractory metals, consider using a rod-shaped melt. And that's an effort to control the thermal conductivity through the material, limit the thermal conductivity, and get as much energy into these materials as possible. Fixed focus beam for refractory metals. This concentrates the energy on the material and it minimizes or maximizes the rate for the power usage. Number two is sweep to pre-melt most materials or most metals. And generally, again, as I said, I like a nice smooth surface to start with when I'm doing E-beam evaporation, and it usually yields the best results. So some materials like aluminum, I can just put the pellets in and ramp it up normally. And as the melt goes on, if I'm sweeping, the aluminum will melt thoroughly and it'll melt well. And I really don't have to do a pre-melt on aluminum. You might see other materials like that as well, and it's perfectly fine not to do a pre-melt on them. Again, dielectrics, wide sweep, slow frequency, a diffused beam, and try to set the deposition rate up a little higher, like 2 angstroms a second or 3 angstroms a second. Easier to control that way. Process concerns with E-beam is it's a relatively expensive technique when compared with thermal evaporation. And for that expensive technique, the atoms still have thermal energies, less than 1 eV usually. You can get the material migrating over the crucible liner and interacting with the E-gun. Also, if I'm not careful about the ramp soaks, I can get a lot of spitting occurring when I try to run a film through an E-gun. Certain materials like vanadium and molybdenum will spit, and it's just a waiting game. If I want to run them, I'll keep the power on them relatively long time to do pre-melts and preconditioning in an effort to overcome the spitting that usually occurs with these materials. Most alloys must be co-evaporated, and that's true of E-beam as well as resistive thermal evaporation. Compounds dissociate. Usually with the higher energy levels of an E-gun, it's not really a good idea to whack at compounds. And it really does not work well for organics. I don't know of anybody that tries to evaporate organics with an E-gun. Stable evaporation rate requires a little bit of skill because, like I say, you've got to do the ramp soaks in a particular order or a particular way in order to get a smooth evaporation run. And the only other bad point is that there is a large amount of material needed for the initial melt when compared with thermal evaporation. And that's of particular interest when you're using precious metals. And there's no way really around that. If you're doing E-beam evaporation of gold or platinum, you need to get the crucible liner at least 2/3 full. And that can cost a lot of money. Also with E-beam, it's possible to heat the substrate up to quite high temperatures. There's a lot of papers on cross-linking that occurs on PMMA photoresist with E-beam, and there are ways around that as well. If it ever occurs, let me know or talk to somebody in the know, and they can probably steer you toward a technique that gets you out of that situation. Some common problems with E-beam are usually filament issues or crucible cracking and changing the thermal conductivity. Inconsistent powers, which is usually a problem with poor ramp soak. Power levels that are chosen for the ramps and soaks. The most common problem here is that people think they can reuse the same programs when you're running an auto program. I know a program works well for copper. Maybe I can use that same program for gold. And generally, like I say, the ramp soak levels are metered toward a a given material. And as I explained, there can be photoresist issues as well. Pocket limits is, you need to know how to set the pocket limits on an E-gun if you're using it regularly. If you don't know how to set the pocket limits on an E-gun, you really need to ask somebody or have somebody show you this, because it's a very good, useful thing to know how to do. And as I showed you in a slide or two, core drilling through the material is quite possible in an E-gun. Also, if the quartz crystal monitor placement is somewhat questionable, it's easy to get variable film thicknesses. So if I set my quartz crystal monitor for 2000 or say 200 nanometers, and I run a film and I get 200 nanometers the first time, successive runs, I might get a little bit thicker and a little bit thicker and even a little bit thicker film. And generally that's an indication that the quartz crystal monitor is being shadowed either by the melt itself or another piece of equipment that's inside the chamber. And that is it. That was a lot of material pretty quick. Sorry for the pace, but if there are any questions, I can entertain them now. Mark?
Thanks a lot, Rob. Sure, appreciate that. Would temperature-controlled source be useful for all resistively evaporated materials?
Generally, no. It's a temperature-controlled source is expensive when compared with a boat, and they have their drawbacks as well. They're relatively delicate. They're subject to a given regime, so you'll have one temperature-controlled source for, say, 0 to 600 degrees C materials, and then you have another temperature-controlled source for 600 to 1200 degrees C, but it doesn't go too much more above 1200 degrees C. So there's a thermal limit on the temperature-controlled sources as well.
The picture you showed looked kind of like a little mini Knudsen cell. Is that how you'd think of it?
Yeah, absolutely. Let me make everybody dizzy and go back to that. Oops, there we go. So it's sort of like a mini Knudsen cell. That's exactly right. Specially fabricated to hold a crucible. The crucible again sits on a thermocouple, and you have the coiled heater around the crucible to heat it up.
To reduce chemical reaction to the source during venting, do you have any recommendations of a waiting period after turning off the power to the source?
It just depends on the source and the material itself, but generally as a rule of thumb, I wait 20 minutes. I mean, sounds like a long time, but 20 minutes on either a resistive thermal setup or an E-gun is quite sufficient to cool the material down to the point where generally it's going to be at room temperature or slightly lower, depending upon the chiller set point, and it's less likely to interact with the ambient atmosphere.
Are there any materials you would run in an E-beam system without a crucible? Without a liner?
You know what? It just depends. Absolutely. You can run material directly in the hearth pocket. Some materials are going to interact with copper, like aluminum and silicon. But I have run a lot of materials directly in the pocket, especially when I'm doing production. When I worked in the production optics industry, most of our materials stayed set. In other words, we were always running, say, germanium out of pocket number 1 in an E-gun. So I didn't need a crucible liner. I just put germanium directly in the hearth pocket, and that's how I ran it. The drawback to that, or the downfall to that, is that there's possibility of cross-contamination if I decide to change the material in that pocket. I still might get a little germanium through that melt.
Does the pellet size affect the deposition rate and uniformity for sublimating materials?
It will. And the reason, well, look at it this way. I try to get as dense, one way or another, I try to get as dense material packing as possible. And that helps me with the thermal conductivity issues. And generally, as a rule, the smaller the pieces, the better, as far as I'm concerned.
Do you have any additional comments on E-beam evaporation of oxide materials?
Only the ones that I've covered. Make sure the crucible liner is electrically conductive. Make sure you use a low voltage as possible in the E-gun, and generally mine can go from 4 kilovolts to 10 kilovolts, and I usually use 4 kilovolts to do oxides. And a wide sweep pattern at as large an amplitude as I can afford, and as slow a frequency, because the more the beam crosses the center, and trust me when I say there are pre-programmed center cold, i.e. it doesn't cross the center, it always crosses the center. No matter what the manufacturers, and I've tried just about every E-gun under the sun, no matter what the manufacturer says, the beam is always going to cross the center, and that's where I'm going to core drill through on oxide materials.
Question about thermal conductivity between crucible liner and the hearth. Is it in general a good or bad idea to use a spacer between the liner and the pocket?
Yeah, I mean, as I pointed out in E-beam, if you understand the thermal conductivity path through the gun, you can do things like add a spacer. So that, what does the spacer do? It acts as a thermal break in essence. It's another thermal interface. So what that does is it slows down the thermal conductivity through the material, and it keeps more of the heat from the E-beam in the material itself. So for a given rate, you can run at a lower power now. Again, with a lot of knowledge comes a lot of responsibility though, because think about it this way. When the crucible liner is in the hearth, it's relatively cold, and the interactions between the material and the crucible liner are slim to none when the crucible liner is cold. However, when I now space the crucible liner off of the pocket with a spacer, the crucible liner gets hot, and there are interactions between the material and the crucible liner. Chances of that go up as the crucible liner gets hot.
Can you comment on quality of films and variation on an ion-assisted evaporation?
Yeah, I mean, I've used ion assist on a lot of optics, especially when I need low absorbing optics. And basically what that does is it makes a relatively denser film, and I get better N and K values, and I get lower absorption with an ion-assisted evaporation. Basically, it just adds energy to the atoms, and they can compact in closer together, form tighter, denser films, and give me more bulk value properties than without the ion assist. So I don't know how to explain that. But again, with an ion gun, it's quite possible to turn the energy up and do more damage than you are doing good. So it's all about balancing that energy equation, only using enough energy from the ion gun in order to increase the film density, smooth the film out, and not too much energy as to where you're blowing the film back off the substrate.
For insulator material sources in E-beam evaporation, say like SiO2 or aluminum oxide, the beam tends to get large even at 7,000 volts. Is there any comment you could make on the importance of focusing the beam and how to do it?
Yeah, for insulating materials, I don't want the beam to focus in essence. And if you can envision, I'm a an irregular shaped piece of silicon dioxide. Maybe I'm, I don't know, 2 millimeters in diameter on average. And I've got all sorts of jagged edges to me. My thermal conductivity between myself and the piece that's underneath me is quite low. So if I were to focus the energy of the beam, say if I could, down to 2 millimeters, so that all the beam is now on that one piece of silicon dioxide, it's going to sublime and it's going to blow off at quite a rapid rate. No matter how good my PID loop control is, if I get many of those events where I get rapid evaporation or rapid sublimation of the material, it's going to be very hard to control the rate. So in general, what I'm trying to do was heat up the material as evenly as possible on the surface so that I avoid this rapid kind of sublimation and popping or rapid increases and decreases in the rate during the course of the evaporation.
For platinum evaporation, it tends to form a pit at the source after one deposition. Is there any sweep pattern that you can suggest so that it doesn't require such a high power? Or any other problem solving that you would suggest for platinum evaporation?
Are you using a spacer underneath the crucible liner? If you use a spacer underneath the crucible liner, I think that'll even it out a bit because the material will get hotter and stay hotter for a given power level.
Okay. I have someone who would like to chat with you about some specific issues that they have. I assume that you're happy to take questions from people about any of their specific evaporation issues. How would you prefer they initiate a contact?
Email address. My email address is just simply ROBB, so it's Rob with 2 B's at lesker.com, Lesker.com. I'll go back to that slide if I can. And up on the screen is my email address, and that's the best way really to get a hold of me.
Would you comment about any fundamental difference between carbon, graphite, and fabmate?
From a practical standpoint of view, there's not much difference. Regular carbon is a little bit cruder and ruder and more inclined to give you a little bit of dirt in the melt as you're doing the evaporation run. Pyrolytic graphite or fabmate kind of cleans that effort up a bit and reduces the amount of cross-contamination or the amount of carbon that can get back into the melt. The idea there is, though, that if you hit the crucible liner with the beam, I don't care what kind of, if it's graphite, carbon, fabmate, if you hit the liner with the E-beam, you're going to generate the material getting into the melt. And, I just wanted to say that usually since gold does not wet or platinum does not wet the graphite or fabmate, generally what happens is you'll develop a scum layer on top of the melt of graphite. And you can absolutely clean that off just by getting the cold slug and wiping it with a clean room wipe. Some people even use something like isopropyl alcohol or something of that nature and wipe the carbon right off of the melt. The graphite is less dense than the gold or the platinum. It'll float to the top. And again, it won't wet or won't stick in the metal. So you're able to just wipe it right off.
That's very helpful. I'm going to now give in to your baited question early on. Do you have any additional comments on proper crystal monitor setup?
As a rule, and let me blast all the way down to my presentation because I just closed it out. Way to go, Rob. Yeah, I don't know how to get back to it, and I'm not even going to bother. It'll take too long. But at any rate, generally as a rule, I always have 2 quartz crystals in an evaporation setup. If I'm doing E-beam, I have one to control the rate of the E-gun, which is in the PID loop control with the power supply for the E-gun. And the second one is up high and as normal to the melt as I can get it without getting in the way of the substrate. And this is controlling thickness. So the idea is I have a quartz crystal monitor to control thickness that's near the substrate, and I have one a little bit lower to control the rate with the E-gun. That is my preferred setup. If the quartz crystal monitor, if say I only have one quartz crystal monitor to control the E-gun, if I get it at a very steep angle in relation to the pocket, like I'm trying to get it between the E-gun and the substrate, and if it's at too steep of an angle relative to the pocket, as the melt goes down lower in the pocket, the quartz crystal monitor can be shadowed by the crucible liner itself. And generally what happens is the rate will go down on the quartz crystal monitor, but you're still getting a higher deposition rate at the substrate. And that's the instance of what I explained before is after successive runs, you'll get thicker and thicker film as the material level gets lower and lower in the crucible. Poor explanation, I understand, but I apologize.
And back to one of your early comments, because of the lack of reproducibility as well as reversibility, what might one want to avoid if they don't want to die using an evaporation system?
Make sure you understand the equipment, okay? Make sure you know what's electrically hot and what's not electrically hot. Make sure you understand what the system looks like when the power's on, what's required for the power supply to be on. Second question is it possible to vent the system and still have the power supply on? If that's possible, you've got a very dangerous system there. So all these PVD systems should be interlocked out so that when you vent the system, the power supply automatically turns off. So there's no way to touch the source, the E-gun, the resistive evaporation boat, there's no way to touch it when the system is at atmosphere because the interlock automatically shuts power off to the source. That is step 1, rule 1. If you and it's possible to bypass interlocks. If you bypass the interlocks, the greater the risk of you getting hurt by the system.
We also occasionally have people who are doing specialized experiments with heating or bias, and they bring in their own power supplies that are interlocked to nothing of the system. So I appreciate you clearly reminding people that manual units tend to obey us, and a check sheet and very precise care sure beats getting shocked.
Yes, absolutely. It'll extend the lifespan considerably if your one is careful.
Very good. I thank you again for joining us today. Thank you everyone for joining in the talk.
Hey, I'm usually much better in person, so I apologize.
I think you've done very, very well. This is the way of the world these days.
Yes, it is. But I appreciate the opportunity. And again, I invite you to contact me directly if you have any questions.
Thank you. You've been listening to Rob Belan from Kurt J. Lesker. My name is Mark McCollum from HMNTL. And you're welcome to contact me if you have any questions about the seminars or anything that happened today. I'll be glad to put you in touch with the right people and do anything that I can to help. That's it for today. Thank you.
All right, take care. Thank you, Mark.